A junction field effect transistor, JFET, is built from a single crystal of semiconductor material, most commonly silicon. Think of a thin straight pipe made of a conductive material. That pipe is the channel. In an N-channel JFET, the channel is heavily doped N-type silicon, which means it has many free electrons. At each end of the pipe are two metal contacts called the source, where electrons enter, and the drain, where they leave. Surrounding the middle portion of the pipe is a region doped with the opposite type, P-type for an N-channel. This surrounding region forms the gate. The boundary between the N-channel and the P-gate creates a P-N junction. Just like the wall separating two rooms that only lets water, carrier flow, leak through when a pressure voltage is applied. When no voltage is applied, a thin depletion region, water-free zone, exists naturally at the junction, slightly narrowing the channel. The whole structure is typically encapsulated in a ceramic or plastic case, with three metal leads that poke out for external connection. The JFET symbol is a simple line drawing that resembles a little arrowless triangle pointing from the source to the drain, with a line the gate touching the side of the triangle. For an N-channel device, the gate line is drawn with a short perpendicular stroke and no arrow. For a P-channel, the same drawing is used, but the device is labeled P-type. The three pins are: Gate G, the control terminal attached to the P-type region; Source S, where charge carriers enter the channel; Drain D, where carriers exit. Orientation matters when you place the part on a PCB. The tab or a beveled edge on the package usually marks the drain side, and a dot on the silkscreen indicates the source. In the common T092 package, looking at the flat face, the pins from left to right are typically DGS for an N-channel JFET, but always check the data sheet because manufacturers may differ. A JFET is a depletion mode device, which means it is normally on conducting when the gate source voltage VGS is 0. Applying a reverse bias voltage to the gate, making VGS negative, for an N-channel widens the depletion region much like squeezing a garden hose with a clamp. As the clamp tightens, the water flow drain current ID reduces. When the depletion region expands enough to completely block the channel, the device reaches pinch-off. The gate voltage at which this total closure occurs is called the pinch-off voltage VP or VGS off. Beyond VP, the channel is fully cut off, and only a tiny leakage current flows, so the JFET behaves like an open switch. Mathematically, the channel resistance increases with the width of the depletion region, and the current follows the famous quadratic law. ID equals IDSS times open parenthesis 1 minus VGS, divided by VP close parenthesis squared for VGS magnitude, less than or equal to VP magnitude, where IDSS is the maximum drain current when VGS is 0. This relationship shows that a small change in gate voltage produces a predictable change in current, which is the basis for amplification. Static IV curves are the road maps that tell you how a JFET behaves. Transfer characteristic, ID versus VGS, plotting ID against VGS with a small drain source voltage, yields a downward curving parabola that starts at IDSS when VGS equals 0 and goes to 0 at VGS equals VP. This curve shows three regions. Cutoff VGS less than or equal to VP, ID approximately 0, the device is off. Linear ohmic region, absolute VGS less than absolute VP and low VDS, the channel behaves like a resistor. ID varies linearly with VDS. Saturation active region, absolute VGS less than absolute VP and higher VDS. ID becomes almost independent of VDS and is dictated by the VGS controlled channel width. Output characteristic, ID versus VDS, for a fixed VGS, sweeping VDS gives a curve that initially rises linearly ohmic region and then flattens out saturation. The point where the curve bends is called the pinch-off point for that gate bias. By drawing several curves for different VGS values, you can see how the saturation current drops as VGS becomes more negative. These graphs are analogous to a traffic light. The gate voltage is the controller that tells the road, channel, how many cars, electrons are allowed to pass, while the drain source voltage is the pressure that pushes the cars forward. Key parameters that quantify a JFET's behavior are: IDSS maximum drain current with VGS equals 0. It is set by the channel doping and geometry, similar to the maximum water flow through an unclamped hose. VP or VGS off gate source voltage that reduces ID to 0. It is a negative value for N channel and positive for P channel. Transconductance GM, how effectively a change in VGS changes ID. GM equals DID divided by DVGS equals open parenthesis 2 times IDSS divided by absolute VP close parenthesis times open parenthesis 1 minus VGS divided by VP close parenthesis. At the point where VGS equals VP divided by 2, GM reaches its peak value. GM max equals IDSS divided by absolute VP. Output conductance, GD small signal slope of the IDVDS curve in saturation, reciprocal of the output resistance RO. GD equals 1 divided by RO equals partial ID divided by partial VDS, at constant VGS. In an ideal JFET RO is very large, GD is tiny, meaning the current hardly changes with VDS. RDS on a channel resistance in the linear region, approximately VDS divided by ID when VGS equals 0. These parameters are like the specifications on a water pump. IDSS is the maximum flow, VP is the pressure needed to shut the valve, GM tells you how quickly flow changes when you turn the valve a little, and RO tells you how stiff the pump is against pressure changes. For small signal AC analysis, we replace the JFET with an equivalent linear circuit that works around a chosen bias point VGSQ and IDSQ. The classic model consists of GM.VGS, a dependent current source from drain to source where VGS is the small AC voltage on the gate source terminals. This source represents the change in drain current caused by the gate voltage. RO, a large resistance from drain to source, representing the finite output conductance GD. RG, the resistance looking into the gate, often very high because the gate source junction is reverse biased. RS and RD, the external source and drain resistors that may be part of the circuit. Deriving GM from the bias point uses the quadratic expression for ID. GM equals partial ID over VGS equals open parenthesis 2 times IDSS divided by absolute VP close parenthesis times open parenthesis 1 minus VGSQ divided by VP close parenthesis. If the device is biased at the point where VGSQ equals VP divided by 2, then GM simplifies to IDSS divided by absolute VP. The output resistance is found by differentiating ID with respect to VDS in the saturation region. Because ID is almost flat, RO approximately equals 1 divided by GD is typically tens to hundreds of kiloohms for silicon JFETs. This model is like a spring damper system. The spring constant GM tells how much force current you get for a small displacement voltage, while the damper RO shows how much resistance the system offers to motion voltage changes. JFETs can be wired in 3 basic amplifier topologies, each giving a different voltage gain and input/output impedance. Common source CS-gate is input, source is common, often grounded through a resistor RS, drain provides the output. The small signal voltage gain is a V approximately negative GM times RD parallel RO if RS is bypassed by a capacitor. A V approximately negative GM times open parenthesis RD parallel RO close parenthesis divided by open parenthesis 1 plus GM times RS close parenthesis, if RS is not bypassed. The negative sign means 180-degree phase inversion, similar to flipping a seesaw. Common drain source follower CF- drain is common, gate is input, source is output. The gain is close to unity. A V approximately open parenthesis GM times RS close parenthesis divided by open parenthesis 1 plus GM times RS close parenthesis, approximately 1 minus 1 divided by open parenthesis GM times RS close parenthesis. This stage provides high input impedance and low output impedance, useful as a buffer. Common gate CG-source is input, gate is grounded or at a bias voltage, drain is output. The voltage gain is approximately a V approximately negative GM times RD, no inversion. The input impedance is low, approximately 1/Gm, making this stage good for high-frequency applications. In all cases, the gain depends on Gm, which itself depends on the bias point and the load resistances. Think of Gm as the strength of a lever. The larger Gm, the more the output moves for a given input movement. Temperature has a noticeable effect on JFET behavior because semiconductor carrier concentrations change with heat. IDSS usually increases with temperature, roughly 0.5% to 1% per degree Celsius for silicon, because more electrons are thermally generated, so the channel conducts more even with the same gate bias. Vp becomes less negative. Its magnitude shrinks as temperature rises, meaning the device reaches pinch-off at a smaller reverse gate voltage. Gm is proportional to ID, so it also rises with temperature, but the change in Vp partially offsets this effect. RO, output resistance, tends to decrease because the increase in ID makes the saturation region slightly more sloped. Leakage currents, gate source and gate drain reverse currents grow exponentially with temperature, introducing more noise and possibly shifting the bias point. Designers therefore add temperature-compensating bias networks, for example a resistor divider with a thermistor, or choose devices with a low temperature coefficient when precision is required. An everyday analogy is a bicycle tire. As the air gets hotter it expands, so the pressure analogous to Vp changes, affecting how the tire, the JFET, rides. Overall, a JFET that works well at 25 degrees Celsius may deliver 10 to 20% more current at 75 degrees Celsius, and the designer must either accommodate the gain shift or stabilize the bias. Derive the expression for ID as a function of VGS for an N-channel JFET operating in saturation. Start with the depletion width model. The channel thickness reduces linearly with reverse gate bias. The effective channel conductance is proportional to the square of the remaining width. This leads to the quadratic law, ID equals IDSS times open 1 minus VGS over VP close squared for VGS greater than or equal to VP, absolute VGS less than or equal to absolute VP. Write the channel charge per unit length Q equals C prime times open W minus 2x sub D close, where x sub D is depletion width. Current I equals open W over L close times mu times Q times VDS. But in saturation, VDS is large enough that the channel pinches off, making VDS drop out of the expression. Substitute x sub D proportional to absolute VGS and simplify to obtain the above parabola. A JFET has IDSS equals 10 mA and Vp equals minus 4 volts. If it is biased at VGS equals minus 2 volts, calculate ID, Gm, and the small signal voltage gain for a common source stage with RD equals 2 kiloohms, ignoring RO. A solution: ID equals 10 mA times open 1 minus 2 volts over open minus 4 volts close squared equals 10 mA times open 1 minus 0.5 close squared equals 10 mA times 0.25 equals 2.5 mA. Gm equals open 2 times IDSS divided by absolute Vp close times open 1 minus VGS over Vp close equals open 2 times 10 mA divided by 4 volts close times open 1 minus 2 volts over open minus 4 volts close equals 20 mA over 4 volts times 0.5 equals 5 millisiemens times 0.5 equals 2.5 millisiemens. Voltage gain of V approximately negative Gm times RD equals negative 2.5 millisiemens times 2 kiloohms equals negative 5.0, approximately negative 5 volts per volt. Compare a JFET and an enhancement mode MOSFET in terms of input impedance, biasing requirements, and typical applications. Answer outlined. Input impedance: both of gate source junctions reverse biased, giving very high DC impedance. The JFET gate is a PN junction. The MOSFET gate is insulated by silicon dioxide, often yielding even higher impedance, gigohms to teraohms. Biasing: JFETs are naturally depletion mode. They conduct at VGS equals 0, so a simple bias resistor can set the operating point. MOSFETs are usually enhancement mode, requiring a positive VGS for N-type to turn on, so a gate drive voltage source is needed. Applications: JFETs excel in low-noise front ends and analog switches where a simple bias is desired. MOSFETs dominate digital logic and power switching because they can be fully turned off with zero-gate current and handle higher voltages. These sample problems help students practice model derivation, numeric substitution, and conceptual comparison, core skills for any electronics exam.